In the previous class, we studied the simple harmonic oscillator and damped harmonic oscillator. The simple harmonic oscillator has the equation of motion of the form, and the solution was sinusoidal function, this kind of form. This was amplitude and angular frequency that is determined by square root of k over m, and phase is free, and these two free numbers can be determined by once we know the initial conditions, values of the initial position and velocity. And if we substitute this answer to compute the kinetic energy and the potential energy, the sum of these, that is the total mechanical energy, was preserved. So it is constant of time. On the other hand, if there is a damping force, that is a minus bx dot, if we multiply the velocity, then we obtain the power due to the damping force, and this power is negative definite. Because of this, the total mechanical energy decreases as time goes on. The actual equation of motion is of the form equals 0, and gamma equals b over m, and omega 0 is square root k over m. Because of this factor, this contribution, negative contribution to the power, total mechanical energy decreases. If we look at the solution, it is proportional to minus 1/2 gamma t, and it depends on the situation. The solution is classified into three cases. The three cases are first of all, underdamped, then in the limit, in the range 1/2 gamma is smaller than the characteristic frequency of the corresponding simple harmonic oscillator. In that case, exponential factor and multiplied by the sinusoidal function, the amplitude, the displacement is oscillating, but the magnitude, the size of the oscillation is shrunken as time goes on because of the exponential 1 minus 1/2 gamma t factor. So as time goes on, it makes a complete stop. The other extreme case is overdamped case. That is, for the 1/2 gamma is greater than the characteristic frequency omega 0. In that case, there is no way of oscillation. Instead, the answer is a linear combination of the two powers. One is gamma plus gamma prime t, and the other is gamma minus gamma prime t, and gamma prime is square root gamma square minus, what's that? 2 omega squared. Am I right? Because in this case, omega prime equals omega squared minus 1/2 of gamma squared, and gamma prime is a reversed one. Gamma 1/2 gamma prime equals 1/2 gamma squared subtracted by omega 0 squared. I pull out the 1/2 gamma, then it becomes 1 minus 2 omega 0 over gamma squared m alpha. Oh, I'm right. So because gamma prime is greater than 0 and less than gamma, it is these two vectors are positive definite. So linear combination of these two gives the answer that is strictly decreasing. There is no rise up in the middle. So overdamped case is for this. And on the border between these two cases, we have omega 0 is 1 half gamma. That is the case called critically damped motion. In the critically damped motion, we had the double root for the quadratic equation for the characteristic frequency. Hence, the solution we find for the first time we find only a single solution. We have found a way to find the exact solution for this critically damped case, that is C0 plus C1t. And because of this, still there is no way of oscillation. Even though there is no oscillation, in case we have a linear term in here, there's a little bit rise up, but it never returns. This is exponential and this is t, and because of it, there is some maximum point and coming back. So local maximum may arise if we have a linear contribution in the critically damped case. But anyway, there is no oscillation because sinusoidal function does not appear as a product. In any case, the contribution of this damped harmonic oscillation, the solution is always decaying to 0 as t goes to infinity. So if we have enough time, the system makes a complete stop. So how can I continue this oscillation? The only way of keeping the oscillation against the presence of the damping force is the driving force. Simplistic driving force that can be applied to a simple harmonic oscillator, the driven damped harmonic oscillator, is a sinusoidal function. Because the equals 0 case that without driving force has a sinusoidal and exponential product is the solution for that problem. But what we want to do is to erase the decaying factor and keep it oscillate just like the system oscillates with the original characteristic frequency in case B equals 0, B or gamma equals 0. It's our simple choice is the choice for the driving force is the sinusoidal function. And it is easy to prepare such kind of input because if we, for example, we have a motor and it can rotate, and by attaching crank, the rotational motion can be transformed into the oscillating translational motion. So this is a simple choice for the driving force applied to the damped harmonic oscillator. There are three choices. The first one is a cosine, sine, but actually cosine and sine are correlated. The translational operation will give the two waves overlap. Another contribution will be exponential e to the I omega t, but actually this one contains both the cosine and sine in it because cosine omega t plus sine omega t. In fact, this exponential, the imaginary part does not exist at all in nature. However, we can always project out the real or imaginary part. The introduction of a pure imaginary number I is for a kind of a basis. For example, in the Cartesian coordinates, vector x is decomposed into x comma y. And this I is, right now, we do not need in the end, because from this we construct a complex number I, x plus iy. What we are really interested in is the either real part or imaginary part. So anyway, these three choices are equivalent, and we will find that the solution for the driven damped harmonic oscillation, we can apply any of the three choices. The summary of damped harmonic oscillation, that I think we have explained enough, but let me briefly review. Gamma is the coefficient B over M that represent the damping force, and omega 0 is the characteristic frequency that is the solution for the eigenvalue equation or characteristic equation for the characteristic frequency equation for the simple harmonic oscillator. And we had omega prime and gamma prime. Omega prime is a useful parameter that determines the angular frequency of the oscillating vector. This is exponential factor, and this oscillating vector has the angular frequency omega prime. As we can see, that omega prime is less than omega 0, that corresponds to the simple harmonic oscillator. So, because of that, the period is a little bit longer than the period of a corresponding simple harmonic oscillator. There is another parameter gamma prime that is just a reversed order. This one represents the correction term for the decaying vector for the overdamped case. The sum will be the answer for the overdamped oscillation. However, in any case, as t goes to infinity, these effects are called evanescent, that is decaying as t goes to infinity. Here, we can see the displacement and velocity for underdamped, overdamped, and critically damped motion. In any case, because of these exponential factor, answer, the solution decays, whether it is oscillating or not. So the fact is that as t goes to infinity, the solution for the damped harmonic oscillator decays to 0. Let us consider a general solution for the driven oscillator. Driven oscillator has a right-hand side non-zero. Instead, non-driven system has the equation of motion of the form E equals 0. All the left-hand side contribution depends on x, or it's a first order or second order derivative. And right-hand side is 0. So the characteristic equation for this, if we substitute this trial solution, is a quadratic equation for lambda. That's the reason why we had two solutions. Sure, in case we have double root, then we have a way to to find out the second solution. Anyway, either lambda 1 or lambda 2, this one should be a solution for this. That is called the homogeneous equation solution. And this one is also solution. And because if we substitute this solution to this equation, we obtain zero. Arbitrary number can be multiplied to have it satisfied. And arbitrary number can still be multiplied. And again, the sum of these two is still the solution to this homogeneous equation. That's the reason why if we had two solutions for the characteristic equation, two eigenvalues, then I can substitute this one, these two solutions, and multiply arbitrary numbers and construct a arbitrary linear combination. This is the most general solution for this homogeneous linear differential equation. In case we know the initial conditions such as x0 and x prime 0, the velocity, then we can determine the two undetermined parameters to be exactly determined by these two constraints. And once we know the homogeneous equation solution, we we consider the case we have non-vanishing right-hand side that is due to the driving force. If there exists a driving force, there is no special way, no general way to find out the solution satisfying this equation. It is case by case. In most cases, we have to find a lucky way, regardless of uh, this bad nature of determining, I mean, the way of finding the solution, there is a no general rule. So usually we find it by accident or copying somebody else's result, something like that. But one of the reasons why we stick to sinusoidal function for the driven oscillation is in that case we know the answer. Just the same function with a different phase a little bit and a different amplitude, except that the basic structure of a sinusoidal function should be the same. Why? Uh, they just found by trial, substituted, and by accident it became the answer. That's the reason why everybody is copying that return. Anyway, whatever, if you know the particular solution that satisfies the right-hand side, the general solution for the whole equation is the sum of the particular solution and the solution for the homogeneous equation. Because a solution for the homogeneous equation does not give anything, zero. So right-hand side is f of t. I can make a right-hand side f of t by substituting x of p, that is particular solution, but I can add general solution for the homogeneous equation because it always gives zero. So it doesn't change the right-hand side at all. So this is the most general solution for the non-vanishing right-hand side equation. That is for the non-homogeneous equation. Non-homogeneous equation. And as I stated repeatedly, this is the solution for the driven damped harmonic oscillations. And this is driving force. Red one is driving force with the normalization the same as the final result. or this is the okay. So the up to normalization, the red one is the driving force. And you can see at relatively small values of t, there is some big difference between the driving force. Why? This is because of homogeneous equation solution that has exponential minus 1 half gamma t, sometimes oscillating. In the case of underdamped case, the overdamped case, no oscillation. Overdamped, no oscillation. But however, you can see what it is. This is due to the driving force. So after we apply the driving force, there is some big difference between the driving force and the actual solution. But as time goes on, this transient effect coming from the homogeneous equation decays exponentially, and the solution converges to the solution with the particular solution. So it's better to say it is a particular solution. The red one is a particular solution. So particular solution plus a solution for the homogeneous equation is the general solution. But as t goes to infinity, this contribution disappears and only the particular solution, that is a sinusoidal one, just like the driving force, survives. How to find the solution? There's no way in general. However, our our driving force is we have restricted ourselves with the MA0 cosine or sine or e to the I omega t. We have restricted ourselves to consider this kind of input only. Then the trial solution will be just a trial particular solution, I mean. Particular solution will be of the form sine, cosine, exponential, except that we must allow the phase shift. The reason is that equation of motion is omega 0 square x. This is for simple harmonic oscillator, and we have a special piece, 1 and A0, either cosine, sine, exponential. In this case, no derivative or double derivative. Sinusoidal function cosine double derivative is minus omega squared cosine itself. Sine double derivative, again minus omega squared sine. Exponential double derivative, still omega squared. So these are in phase. Just x and x double dot, that they are in phase. In phase. However, as far as the first order time derivative term is concerned, it is out of phase. It is not, it has some phase difference. Because cosine omega t derivative is a minus omega sine omega t, and sine omega t's derivative is omega cosine omega t. So this is not cosine anymore, it is sine, minus sine. And this is not sine anymore, it is a plus cosine. Because of that, we must allow some phase shift in the answer. Okay? I believe everybody knows this, so let me pass. We have already considered this in the well ahead when we consider two-dimensional motion. And in summary, 2D two-dimensional Euclidean space with Cartesian coordinates x and y and x plus iy, this complex number, they are equivalent. So they have a very similar nature as far as the geometry is concerned. So 2D polar coordinates, x, y components can be expressed in terms of radius and polar angle. This is an azimuthal angle in three-dimensional case. And we can make use of Euler's formula. This one is equivalent to write the Cartesian coordinates in terms of polar coordinates. This one is equivalent to write c equals r e to the I theta. This r cosine r sine. This is r cosine plus the imaginary part is r sine, but they are equivalent. Because of that, this multiplication is something like in two dimension multiplying rotation matrix r beta and r alpha, something like that. So rotate, we keep the axis of rotation and rotate twice with alpha and beta angle. The result is a single rotation with the sum of the two parameters. And the complex conjugate is the negative angle. That means, sure, if there is a over this modulus, non-vanishing modulus, then complex conjugate has an inverse of modulus, reciprocal of the modulus, and argument, this is angle, becomes negative to them make them once they are multiplied together, it is just a multiplicative identity one. So let us substitute this trial solution. It should be cosine, and we have to take into account the possibility of phase shift. Then we can obtain the answer. Okay, why don't we substitute this one into the differential equation of motion. So because they are of the same kind, let me write it in this form. What's that? This one becomes omega 0 squared minus omega squared x plus gamma x dot. Omega 0 minus omega squared x trial solution. And gamma x dot. Because it is cosine, I have minus and omega chain rule. And cosine became sine. Okay, I have substituted this one on the left hand side, and right hand side should be this one. What should I do? What I have to do next is I have to combine these one into as a cosine. That is, I need to rescale it expressed in terms of cosine, some angle that is independent of delta, and the sine, some angle. Why? If I pull this out, this is a plus bi, then it is square root a squared plus b squared e to the I delta when cosine delta prime equals a over square root a squared plus b squared, and sine delta prime is b over square root a squared plus b squared. All right, so this is the right reason why I have parameterized with this one with cosine and sine. Then cosine minus sine. Aha. So this one finally can be expressed in terms of this after factoring out the overall modulus. Then square of these two, sum is 1. Right? So that's the reason why I can express this one as either cosine or sine, but we have to replace this one with cosine because my goal is to express in terms of cosine. So this one gives a cosine omega t minus delta plus delta prime. Finally, I find that these two are the same only if delta prime equals delta. That's the answer. So delta prime is determined to be delta, and this one is cosine delta and sine delta. And what is my answer? Substitute this one into the trial solution. We have a omega. What is a omega? This is a omega. This one cancels and this one remains. So the amplitude is A0 divided by the modulus. And phase shift delta can be determined if we know the cosine and sine. All right, this is the case for the driving force is a cosine function, and this is for the sine function. The difference is there's no difference at all. We have substitute this one to find these expressions in a similar manner. The reason why I have positive sign in here while this is negative sign, because cosine's derivative is negative sign. Sine's derivative do not bring in any negative sign for another negative sign. So x dot omega 0 square x dot x plus gamma x dot equals a0 sine omega t. This is the equation. This part is this, and I have substituted this result in x, and finally I have a positive sign in a very similar manner. Now, again, I pull out the modulus of these two numbers, this a and b, and let's see, what should I do? I have to make a sign by combining these two. Then the only way is because this is sine, addition formula works only if this is parameterized by cosine. So cosine delta prime and sine delta prime. And sum of this is a sine omega t minus delta plus delta prime. And this is a0 sine omega t. In a similar manner, this one must cancel. If it is not the case, this is not the answer. This is the only answer. So I have determined delta prime again. Very interestingly, even though the shape of the function is replaced with sine instead of cosine, the functional dependence, the negative delta form, and the value of delta determination, this rule is identical to each other. Identical. Omega 0 square minus omega over square root is cosine in here, and this is also cosine in here. In a similar manner, sine, they are identical to each other. So the way of finding solution for the driving force, either sine or cosine, they are identical, absolutely the same. We can apply this one to sinus of the exponential function. The only difference is it is x e to the I omega t x dot I omega e to the I omega t, and x double dot is minus omega squared e to the I omega t. So this is the difference in comparison with the derivative of sine or cosine. Again, we do the same job. Pull out the modulus, and remaining thing becomes exponential I delta prime. And what's next? This delta prime and delta must cancel. Oh, in that case, still the rule is identical. This is cosine, this over square root cosine, this over square root sine. So in any case, sine, cosine, exponential. Everything has the same result. Everything has the same result. That's quite important. So we have e to the I delta, that is cosine, plus I sine. And the real part is omega 0 squared minus omega squared, and imaginary part is gamma omega. And divided by its modulus, omega 0 squared minus omega squared squared plus gamma squared omega squared. In the complex plane, angle delta has been rotated from the unit. This unity is just one. So rotation means this cosine is this one and the sine is this one. Okay. So as a result, what we have found is x of t is a0 cosine omega t minus delta or sine omega t 0, 0. Oh, omega, not 0. Omega is for the driving frequency, sine omega t minus delta or e to the I omega t minus delta divided by omega 0 squared minus omega squared plus gamma squared omega squared. Okay, if input is m0 ma0 cosine omega t, the answer is this. If input driving force is sine omega t, then the answer is this. And driving force is e to the I omega t, the answer is this. In all cases, original amplitude is in the numerator. Original amplitude. Driving force, we normalize this to be mass ma and sinusoid, these sinusoidal functions, divided by this denominator. We notice that the denominator is a function of omega 0, that is square root k over m, gamma, that is b over m, and omega. Omega is the frequency. What frequency? Driving frequency. This driving, depending on these two, the amplitude is determined. We can see as omega may run from 0 to infinity. Omega is a 0, then this answer will be in the denominator will be something like omega 0 to the fourth power, right? So a0 over omega 0 squared, that is the amplitude. When we substitute omega equal omega 0, this guy disappears and amplitude becomes gamma omega 0. We consider the underdamped case, omega is greater than gamma, right? 1/2 gamma. So we expect that if there is a big difference, then this denominator is bigger than this denominator. That means the amplitude is magnified in comparison with omega equals 0. In addition, as omega goes to infinity, denominator goes to infinity. In that case, the amplitude vanishes. It is increasing, and somewhere around omega 0, it should have a maximum value and in decays. So this is the shape of amplitude, amplitude as a function of omega or omega zero. We expect that the amplitude can be magnified at some point. We call this one resonance frequency. We are interested in know how to find the resonance frequency and how the resonance is described. For example, the sharp peak or broad peak. They are determined by these three parameters. Let's see. Okay, so let us summarize what we have found. The amplitude for the driven damped harmonic oscillator has a functional dependence depending on omega, that is driving frequency, and omega zero, that is the characteristic frequency for the corresponding simple harmonic oscillator, and damping factor, gamma. And A0 is the amplitude of the driving force. Sure, that is in units of mass of the, where is it? Units of the mass, the driving force, driving force. This one is expressed in terms of MA and sinusoidal function, and this M has been cancelled. So resonance is this. This is the three-dimensional plot. This direction is omega, and we have expressed omega in units of omega zero. So when we vary omega, this one is a squared value, is a positive definite, and when we begin at omega equals zero, this omega zero squared inside. And when it increases omega and around the value at omega equals omega zero, at omega equals omega zero, this one vanishes. So denominator is drastically decreasing. And at that time, its value is gamma squared omega zero squared. So around the region where omega is approximately omega zero, this denominator becomes a minimum value. There's an analytic way to find the place where the minimum appears by taking the derivative with respect to omega. Or we can complete the square in term in this one is omega to the fourth power and omega squared. So with respect to omega squared, there is a quadratic structure. This is style. So we can reorganize this expression and by completing the square. In addition, this side shows the dependence on gamma. When gamma is increasing, and when gamma is decreasing, the peak becomes sharper. And when gamma increases, the width of the peak becomes broader. It is narrow. So narrow and high peak. That is called, this region is called resonance. Resonance. So let us simplify the expression to find the place where the resonance appears. The structure is this, and we are interested in the structure of the expression inside the square root. And we can expand this omega 0 square minus omega square square. That is omega 0 to the fourth power minus 2 omega 0 square omega square and omega to the fourth power. And then we have additional piece gamma square omega square. So we have omega to the fourth power plus 2 times omega 0 squared minus 1/2 gamma squared, right? Plus omega 0 to the fourth power. We can complete the square. Completing the square, which is omega 0, omega squared, this factor of 2 plus here we have factored this with a negative sign, positive sign. So omega squared minus omega 0 squared and plus 1/2 gamma squared squared plus omega 0 to the fourth power, and we need to subtract this one, omega 0 squared minus 1/2 gamma squared squared. All right, so we can simplify this, expand this leading term disappears, and it becomes minus omega 0 squared gamma squared. The negative sign is a positive, and subtracted by 1/4 of gamma squared. So we can factor this gamma squared out, and finally we have this term and this expression gamma squared omega 0 squared 1 minus 1/2 gamma squared. So this value vanishes exactly. This is complete omega dependence, and this is independent of omega. It depends only on the gamma and omega 0. So this one, the value at this one vanishes is the resonance frequency, and the value is omega 0 squared minus 1/2 gamma squared. Okay, so when omega squared is. So because omega is a positive definite, we can take the square root to find the resonance frequency of the driving frequency that maximize the displacement is at square root omega 0 squared minus 1/2 gamma squared. Right? And we have 1/4 here. And this one, what is that? This is omega prime. Omega prime is omega 0 squared minus 1/2 gamma total squared. This is omega prime. That is for the, we remember in the underdamped case, we have the solution 1/2 gamma t and cosine psi omega prime t minus delta style. So in this omega prime, for the damped harmonic frequency, characteristic frequency for the underdamped motion for damped harmonic oscillator is this one. All right. So we have a resonance frequency, and this value, at when we substitute omega r in here, this one disappears, and amplitude becomes A0 minus gamma squared omega prime squared. So A0 over gamma omega prime. This is the amplitude. We can see the amplitude of resonance frequency is maximized and then decreases, right? The blue one represent the height, this amplitude is all the same. With the same input, the output displacement is maximized, the amplitude is maximized at the resonance frequency. So what an effective output it is. So that's the reason why we research for resonance frequency to maximize the behavior. Next, we consider the velocity amplitude. Velocity x of t equals this one is proportional to a0 and square root and cosine omega t minus delta. This is the so where is omega 0 square minus omega square minus plus or gamma square minus square. Okay. If I take the derivative, time derivative, we have the velocity x of t, and what we have is sine is replaced with cosine is replaced with sine, and I have additional omega dependence in the numerator because of the chain rule. The denominator is same. So what we want to do is find out the condition for the maximum value for this amplitude, resultant amplitude for the velocity. That one can be done by taking the partial derivative of this function with respect to the driving frequency and search for the place where its derivative becomes a zero, flat. So increase somewhere and becomes flat and decrease some maximum value. Actually, this condition is for an extremum value, but in this case, we'll find that if we substitute the value at derivative vanishes, then you will find that it is indeed the maximum value. And actually, if we take the derivative of this expression, it is completely factorized. Numerator is completely factorized. And we search for the omega r, and omega r is indeed, it is positive definite, positive definite. The only solution is omega r equals omega 0. So in the case, if we consider the velocity, the answer is the characteristic frequency of the simple harmonic oscillator itself. And then the magnitude, the maximum value for the amplitude for the velocity is this one. Omega cancel. So A0 over gamma. So this is for the velocity, the exact omega 0. In the case of displacement, that is slightly shifted down by 1/2 gamma squared inside the square. So we are using so many in our life. When we are young, the swing, when you ride a swing, it decays. But if you apply driving force with the same frequency as the characteristic frequency of this pendulum, then you keep riding the swing. Your electronic appliances uses full use of resonance frequencies. And if you dial the channel and the resonance appears and the signal is maximized to get the specific channels transmitted information. Recently, most of us are using NFC device, using the smartphone, and this RFID make use of physics of resonance. And there are so many things that are applications of the resonance, and these are the carbon copy of what we have done with the resonance. This RLC circuit. In this next semester, you will learn how to write this equation for the circuit equation. Is a equation for the potential of the electric circuit. It is exactly the same as what we have done with mass, damping force, and restoring force, and position. This, this mass is replaced with L, that is a inductance of an inductor, such as coil, and R is the resistance of the resistor that spans energy, and 1 over C, E represents string force, that is capacitor that contains the electric charge in it. So simple rescaling with the characteristic frequency omega 0 for the simple harmonic oscillator and gamma for the damping coefficients, we can reproduce everything regarding the driven damped harmonic oscillator in RLC circuit. At the end, we can consider Q factor. Q factor represents the efficiency of a system, a driven damped harmonic system that shows the efficiency. That means you can find an amplitude. For example, use RLC circuit as a current or a velocity of a simple harmonic oscillator, driven damped harmonic oscillator. In that case, there should be a peak at the resonance frequency, but the quality says the if you change the frequency, how fast it grows up and how sharp is this peak is. So uh, a way to parameterize the efficiency of this resonant system is Q factor, and Q factor is defined by this, and this is the resonance frequency, and this is the width. And what is the width? This width represents that this is the peak, this is peak. So you'll find the maximum value of the amplitude. And why don't we cut it half? So half maximum. This is maximum and half maximum. You draw a horizontal line at half maximum. You will meet two places. This is the full width at half maximum. That is called delta omega. And omega r divided by delta omega is called Q factor. It is abbreviation for quality factor. Okay, that's it for today. Thank you.